Okay, for reversible expansion, the essential requirement is that the external pressure must differ only infinitesimally from the internal pressure. Okay, and in order to achieve reversible expansion, the external pressure must match to the pressure of the gas at equilibrium. Okay, so in that case, external pressure will be equivalent to internal pressure and also equivalent to the pressure of the gas at equilibrium. So if we integrate the formula for work equivalent to negative PV, okay, you get this. Okay, and it can be calculated using the ideal gas equation and also van der Waals equation. Now, what's the difference between reversible and irreversible work? So if you see this graph here, okay, this yellow shaded area will show an irreversible work, whereas this graph here, okay, shaded in green as well as in yellow, is reversible process. Okay, so irreversible, the pressure is constant. Okay, so you see here the reversible work obtained from isothermal expansion of gas from Vi to Vf is the area shown under the P equivalent to nRT over V curve, which is this. Okay, for irreversible, okay, you will not get this curve, but you get like this. Okay, like an L here. Okay, so that would be an irreversible process. Okay, noted, when there's a reversible, normally you will see isothermal work. Okay, now to understand this better, we see this example here. Calculate work done if 2 mole of an ideal gas initially occupying a volume of 30 liter at 280 Kelvin allowed to expand isothermally. Okay, isothermally means constant temperature and reversibly, and the volume is 50 liter. How do we solve this problem? Now the keyword here, you see, ideal gas, isothermal, reversibly. Okay, so we use this formula. Remember the curve earlier on? Okay, so we use this formula here. Okay, so we integrate. When we integrate, because there's a change in volume, right? There's a change in volume, we get this formula here. Okay, work will be equivalent to negative nRT ln V over V1. Okay, you have to divide first, then you ln. You don't ln separately. Divide first, then you ln. Okay, so V2 just now mentioned, okay, final volume 50, so substitute 50 there. V1 initially is 30 liters, we put it here. Okay, temperature given 280 Kelvin. R is the gas constant because it's an ideal gas, so it's 8.314 joule per Kelvin mole. And It's 2 mole of ideal gas, so we put it in the formula, so we get negative 2.38 kilojoule. Okay, next is irreversible work. So normally irreversible work, we get a constant pressure. Okay, so irreversible expansion, example here, for an ideal gas at constant pressure, that's the keyword for irreversible expansion, constant pressure of 0.92 atmospheric pressure from initial volume of 30 liter to final volume of 50 liter. So calculate the work done. So formula, okay, W work equivalent to negative PV, okay, change in volume. So if we integrate the formula, so you get negative P change in volume. Okay, so because the volume is given in liter, your answer would be in liter atmospheric. However, work, okay, the unit for work is joule. So to convert liter atmospheric, we times by 101.3 joule per liter ATM. Because why? Because 1 liter ATM is equivalent to 101.3 joule. Okay, so we cancel the liter atmospheric, we get joule. Okay, so the answer, the final answer would be negative 1.86 kilojoule. Work. Okay, I have mentioned earlier, we can do work on the system, or the system can do work on the surrounding. So energy that can be used to change the height of a weight somewhere in the surrounding, okay, and cannot be stored. Okay, work cannot be stored, so it only exists during the process in which work is done. So if work and heat cannot exist, if process has been completed, what happened? Okay, so they are no longer work and heat, but they are called internal energy. So internal energy can be stored. Okay, so we can store work and heat as internal energy. So how to relate internal energy with work and heat? This is the first law of thermodynamics. Okay, change of internal energy equivalent to change sum of change of heat and change of work. Okay, so change of internal energy can be calculated by the difference of final internal energy minus initial internal energy. So we can assume internal energy as bank. Okay, so we store heat and work as internal energy. Okay, so how can we change internal energy? Okay, there's two ways: heating the system or do work. Okay, so again we use the convention positive and negative. Positive means the system get the energy. Okay, if negative means the internal energy is transferred to the surrounding. Okay, simple concept. So the internal energy of the system will change if heat go in or go out from the system. Work is done on the system or by the system. Mass, enter, or leave the system. So these three conditions will change the value of internal energy. So this is the formula relating internal energy as well as heat and also work. So condition number 1, at constant volume means no volume change, okay, or equivalent to 0. So if V is equivalent to 0, okay, which is W, remember W is negative PV, so V 0, so P also 0, so no work is done. So therefore internal energy equivalent to heat here. Second condition, if the pressure is 0, so if P is 0, again no work is done because W is equivalent to P times V. So therefore internal energy equivalent to heat. The third condition, at constant pressure. Constant pressure, work is done because there's a value, okay, so you get this internal energy, heat minus PV. Condition number 4, at variable pressure, work will also be done. Okay, variable pressure means you have to do integration because there would be P1, P initial and P final. Condition number 5, adiabatic condition. Okay, adiabatic means system is insulated, so no heat can be gained or lost. So if no heat can be gained or lost, Q is equivalent to 0. So therefore the internal energy will only be equivalent to work done. Condition number 6, in a cyclic process, cyclic system will return to the original state. So if the system return to original state, internal energy will be equivalent to 0. Alright, let us look at this example here. Electric battery charged by supplying 250 kilojoule of energy, okay, as electrical work, but during the process it loses 25 kilojoule of energy as heat to the surrounding. So what is the change in internal energy of the battery? So how to relate internal energy with heat and work? So we know the formula is U equivalent to Q plus W. Okay, so W is work, so you supply 250 means the positive value, supply it to the battery, so you get it, so it becomes plus, and during the process it loses, so mean minus, so minus Q heat, which is 25 kilojoule. Okay, so therefore we get 225 kilojoule. Alright, next we move on to heat. Heat is energy transferred between system and surrounding due to difference in temperature. Okay, so normally from hotter to a cooler system or surrounding. So heat cannot be stored as heat. Okay, so it exits during the process in which it is transmitted. For example, if heat is being absorbed by the system, then it will have a positive sign. If heat is released by the system, then the sign will be negative. And the symbol for heat is Q, small letter Q, and measured in unit of joule. Okay, although the older unit is calorie. So heat absorbed by a system can lead to different effect. Okay, so it means when heat is absorbed by a system, the temperature of the system may go up, okay, but only one possibility. Okay, certain phase changes may occur. For example, if you have ice, solid ice, and that solid ice absorb heat from its surrounding, then it will change phase from solid ice to liquid water, okay, due to melting. Okay, another possibility is chemical reaction may also take place. Now, how do we measure or calculate when it involves heat? Okay, so the only effect for heat is change in temperature. Then this relationship is used. Okay, Q equivalent to C delta T. Okay, change in temperature multiply with the heat capacity of a system. So heat capacity is specific heat capacity, and the unit used normally joule per Kelvin per mole. Now we can measure heat using one simple apparatus here, calorimetry. Okay, so this is where the reaction will take place. Okay, and the thermometer will measure the change in temperature. Okay, the simplest setup is using styrofoam cup or coffee cup calorimeter. So physical or chemical change in a system produce a temperature change in the surrounding. So this is more sophisticated heat measurement. Okay, a bomb calorimeter. Okay, so bomb calorimeter will have constant volume. Okay, so reaction take place constant volume and constant temperature. So if the volume and the temperature is constant, so no PV work is done because U equivalent to Q plus W. Okay, W is equivalent to PV. So if V is constant, so no PV work is done. So therefore internal energy change will only equivalent to heat. So heat measured with a constant volume calorimeter will equals to the change in internal energy. Okay, so Q is heat capacity multiplied with change in temperature, or if it involve volt and current, okay, we have VIT over time. Okay, so therefore we can calculate C by moving Q to one side. So Q divided with change in temperature will give you heat capacity C. Now what does CP means? Heat capacity, constant pressure. What does EV mean? Heat capacity at constant volume. Now the difference is small if the reaction involving liquid and solid, but if it involves gas, then it will be significantly different between Cp and Cv. So Cp will always be larger than Cv. So when you have heat absorbed by a system at constant volume, okay, when volume is constant means change in volume will be 0. So if V is 0, W equals to PV will be 0. So no work is done on the system. So therefore internal energy will only equals heat, okay, if the volume is constant. Remember this. So if you see comparison between Cp and Cv here, Cp is higher than Cv, okay, for argon gas, helium, neon, okay. For nitrogen, oxygen also the same case. For molecule like H2O also the same case. So this is how we relate Cp and Cv, okay. So Cp larger than Cv, okay. So Cv plus R, ideal gas constant, will give you same value as Cp. Now let us look at example here. Temperature of 15 grams of water vapor increases by 8.61 Kelvin when 0.241 kilojoule of heat is supplied at constant pressure. So what is its molar constant volume heat capacity if it behaves as a perfect gas? So what is being asked here is to find Cv, okay, and you are given Q at Cp. So first of all, write the relationship between Cp and Cv, where Cp is equivalent to Cv plus R, okay. So to find this, we solve this first, okay. So given 15 gram of water vapor using its molar mass, so we'll find mole, which is 0.833 mole. So C is Q over temperature change. So Q given here kilojoule, so we convert it to joule first, okay, and then divide with temperature change, which is 8.61. Now if it only involve 1 mole, then you only stop up to here, but it's only 0.833 mole, so you have to consider 0.883 mole. That's why you see multiply by 0.833 in the denominator here, so that the Cp would be this value here, okay. Now how to calculate Cv, okay, put this here, substitute the value of R with the same unit, you get to solve Cv, okay. Okay, note they are the same unit, that's why initially you convert this into joule. Alright, this example is similar to the previous question. So you are given 0.326 mole of a compound oxidized in a bomb calorimeter having a total heat capacity of 9.96 kilojoule per degree Celsius, and the temperature rose from 25.3 to 34.52 degrees Celsius. How much heat was given off per mole of a compound oxidized? Now look at the question here. We can gain information from the question given. For example here, So it says bomb calorimeter. So when it says bomb calorimeter means constant volume. Okay, so it's gonna be CV. Okay, so the heat capacity is given here. So the C value would be 9.96 kilojoule per degree Celsius. Okay, so because it rolls for every degree Celsius similar to Kelvin also. Okay, so question is asking for Q. So what is Q? Okay, go back to the earlier formula that relate Q with C. So Q will be equivalent to C multiply with the temperature change. Okay, so you are given C there, here. Okay, so 9.96 kilojoule. Please excuse my writing because I'm only using my computer mouse to write this. Okay, so kilojoule per Kelvin. Change it. Let us change it to Kelvin. Times the temperature change. So 34.52 minus 25.3. So you should get 9.22. So 9.22 Kelvin. Okay, right. So we can cross this unit. Okay, per Kelvin times Kelvin, we can cross that. So that gives us a value of 91.83 kilojoule. Now go back to the question. How much heat was given off per mole? So we need to find this in the unit of kilojoule per mole. So means is to be per mole. So what should we do with this value? Because this is referring to this much that react or oxidized. So actually 91.83 kilojoule is referring only to this much compound. Okay, 0.326 mole. Okay, now the question is asking for per mole. So means 1 mole, how much energy will be given off? So how much of this? Sorry, ignore this. Okay, so how much energy here? So therefore this 91.83 divide with 0.326 in order for us to get unit of kilojoule per mole. So 91.83, okay, divide with 0.326, we will get 281.69 kilojoule per mole. Okay, kilojoule per mole. So I'm going to make correction also for the previous example. So previous example also the same. So it tells you that 50 gram of water vapor used. Okay, so meaning that when you calculate the CV, okay, when you calculate CV is referring to 15 gram of water. So you do this approach as well. Okay, okay, I hope that is clear. Alright, let us move on to state function. So what is state function? any property of a system that undergo no net change in a cyclic process. So that is state function, and they only depend on the current state, okay, and independent of its previous history. Later on I explained that. What does this mean? Example of state function are those with capital letter. For example, internal energy U, enthalpy H, and heat capacity C. Okay, the rest that are not capital letter, like heat or work, they are not state function. Means it is dependent on the previous history or dependent on path taken. Okay, for example, let us look here. Okay. Okay, so the reaction is from reactant A, and then the final product would be B. Now, we can do the reaction by converting reactant A directly to give you product B. Or alternatively, we can do several reaction, okay, from A, you see, from A, yellow color, to red color, to blue color, and in the end we get B. Okay, so means this reaction, we are, let's say with this reaction here, we are measuring enthalpy. Okay, enthalpy change. So enthalpy change will only see the difference between initial, okay, the start off, and final. Okay, so it doesn't care which route they take, from A directly to B or even from here, as long as you have this unit, okay, this enthalpy before the process, and then this. See, measure the enthalpy change. Okay, similar to altitude, that's another example of state function. Okay, it depends on the initial altitude and also final altitude. Despite that, you have to climb all that mountain, again climbing all the mountain up to almost the top and going back down. Okay, only consider the initial altitude and final altitude. Okay, next is enthalpy H. Okay, you have covered this in physical chem 1. Okay, so I'm just going to go very quickly on enthalpy. Okay, so you have constant pressure, heat is either being absorbed or released, so that is enthalpy. Okay, we don't measure enthalpy directly, but we concern about the heat added or heat loss by the system. That will indicate the enthalpy. Okay, enthalpy change. Okay, let us look at the formula involving enthalpy. Okay, so enthalpy H equals internal energy U plus PV. Okay, so at constant pressure, if the pressure is constant, the enthalpy change would be equals internal energy change plus pressure multiply volume change. So if the heating is done under constant pressure, that means the external pressure will be equivalent to the internal pressure, means the pressure of the system. So therefore we can rewrite the formula as the enthalpy change equals U, which means Q plus W plus PV. Okay, so because one of the pressure is at the opposite direction, so that's why you have Q minus PV. Okay, here W is equivalent to PV. Okay, PV. So one is external, so PV, work being done. So plus PV here. Okay, so negative PV plus PV cancel off. So you only remain with heat. So therefore, if you see the word constant pressure in a question related to enthalpy, that means to calculate enthalpy, you only need the value of heat Q. Okay, so that's why we measure enthalpy based on the heat gain or heat loss. Okay, so if heat is being absorbed, then it's an endothermic reaction. Heat being released, then you get exothermic reaction, and the sign would be negative. Okay. Okay, so this you know, endothermic you get a positive enthalpy, positive enthalpy value. Okay, exothermic you get a negative enthalpy value because the heat is being released. Now that is constant pressure just now. So let us look at isothermal process. Okay, so this is the definition just now. H equivalent to U plus PV. Okay, so this is at constant pressure. So for a perfect gas, okay, this is the formula. I'm sure you know this formula. PV equals to nRT. Okay, so change in PV here will be also equivalent to change in nRT. So if the amount of gas does not change, okay, we put n outside. Okay, it does not change. Okay, as well as of course the constant gas R. So the one that changes is the temperature. So for isothermal process, okay, this is the keyword. Isothermal process, the enthalpy change would be 0. Okay, so enthalpy is 0 because both the internal energy as well as nRT also 0. Okay, but if there's a change in the mole of gas, okay, this does not apply. Okay, you don't get 0, 0, 0 here. Okay, because there are change in number of mole. Now how to relate enthalpy and also internal energy? Okay, let us look at one example here. So enthalpy change accompany the formation of 1 mole ammonia gas from its element at 298 Kelvin is negative 46 kilojoule. So estimate the change in internal energy. How to relate these two? Remember the formula in the previous slide? H equivalent to U plus PV. So this is the balanced chemical reaction because formation of ammonia from its element is hydrogen and also nitrogen. So looking at this balanced chemical reaction, there would be change in the N value, which is number of mole. Remember, if it involves change in number of mole, you will not get 0 value for enthalpy as well as the internal energy. Okay. Okay, so here we have half mole plus 1.5 mole. So 2 here on the reactant side. Here you have 1. So product minus reactant 1 minus 2. You get negative 1. Okay, so that will be the change in number of mole. So RT has been calculated for you. Okay, using the constant R, okay, multiply by T, where R is 8.314 joule per mole. Okay, and we times by multiply the temperature, which is 298 Kelvin, we get 2.48 kilojoule per mole. So next, the formula relating enthalpy as well as internal energy. Okay, so we rearrange because we want to calculate this. So we get this. Okay, so enthalpy minus -1 mole just now times RT here already been calculated, so we just substitute here. Now how to find the enthalpy change for this reaction? Okay, we check the table. Okay, table of the enthalpy formation of ammonia minus enthalpy formation of sum of hydrogen and also nitrogen. So we only check the enthalpy formation for ammonia because this one, those found in the periodic table, okay, original element like hydrogen and nitrogen will be 0. Okay, so this has been calculated for you. Okay, so we get negative 43.6 kilojoule. Okay, because why? This value is negative. Okay, so let us look at variation of enthalpy with temperature. Okay, so enthalpy, okay, related with heat capacity. Okay, you get this. Okay, so this has been integrated. Okay, we get dH enthalpy equals Cp dt. Okay, Cp means constant pressure. Okay, so if Cp is constant with temperature, okay, so this one is already constant at pressure, but if it is also constant with temperature, then we get this. Okay, change in enthalpy equals Cp multiply change in temperature. But if Cp, constant pressure heat capacity, is not constant with temperature, it must be known as a function of temperature. Okay, for example this. So if the enthalpy varies with temperature, so that means the internal energy would also varies with temperature. Okay, so this is the relationship with heat capacity. See, so therefore du equals Cv dt at constant volume. So if Cv, okay, is constant also with temperature, then the internal energy would equals Cv multiply change in temperature. Not just now, if constant pressure Cp, then it's related with enthalpy. If constant volume, it's related with internal energy. Okay, so if Cv is not constant with temperature, so it may be found using the earlier relationship where Cv equals Cp minus R. Another formula that we can use involving Cp and also Cv would be this one. Cv equals 3/2R. Okay, so therefore Cp would be 3 over 2r, 3 over 2r, okay, for CV, yeah, okay, plus r. So we end up getting 5 over 2r for CP. Okay, so you can use this as well as this. Okay, so reversing a process. Okay, so reversing a process means because the enthalpy only would depend on the initial and final. So you can start from here and up here, or you start from here and up here, but then the difference will be in the magnitude or the sign. Okay, so one would be positive, one would be negative. Okay, very simple. You have covered this also in the physical chemistry 1 subject. Okay, this is one example. Freezing will be the opposite of melting. So the enthalpy change will be the same, except that one of it will be a negative sign. Okay. Okay, again, because it's independent of path taken, okay, you can start off from solid directly to vapor. Okay, sublimation process, or we can go under it can undergo melting first from solid to liquid, and then vaporization from liquid to vapor, but then the enthalpy change will be the same. Okay, so the reaction enthalpy would be the sum of the enthalpy of any sequence of reaction into which the overall reaction may be divided, and that is called Hess law. Okay, you have covered this in if you remember, okay, in physical chemistry 1. Okay, so overall enthalpy change would be considering from the reactant until final. So if you have one to here and another reaction from here to here, okay, another reaction from here to here, but you only consider from here to here. Okay, let's look at example here. Use the enthalpy change for the first two reaction to determine the enthalpy change for the third reaction. Okay, Hess law. Okay, so third reaction would be this one. You can cancel here. Okay, N2 plus 2O2, you get 2NO2. Okay, and then it's being reversed. Okay, so how to calculate that? So given to you the enthalpy change for each reaction here. So from here we can find out the enthalpy change for the third one. Okay, because it's reversed, after adding this, we reverse it. Okay, so 67.6 kilojoule will be the enthalpy change for this third reaction here. So this would be another example. Okay, so methane, when burned in oxygen, okay, to form carbon dioxide and water vapor, you get, okay, from here to here, so it will be negative 802 kilojoule. Okay, enthalpy change. But if that water vapor here, okay, forming liquid water vapor instead, what would be the enthalpy change? So means it is asking from this point here to this point, so we add this with this to give you enthalpy change here. Okay, so next would be standard enthalpy of vaporization. So you will see symbol here, triangle symbol, VEP. Okay, and because you see this symbol here, it is indicating standard. Okay, so standard enthalpy vaporization. Okay, it means enthalpy change per mole when a pure liquid at 1 bar vaporized to a gas at 1 bar. Okay, so if you have 1 mole of water, okay, liquid water, okay, vaporized to 1 mole of gas, water vapor. Okay, the enthalpy change per mole, okay, standard, okay, at 370 Kelvin would be positive 40.66 kilojoule per mole. Okay, next would be standard enthalpy of fusion. So you will see a triangle shape here. Fuse enthalpy. This symbol is indicating standard. Okay, conversion of a solid to a liquid. Okay, example here, solid ice H2O to liquid water. Okay, so you get a positive. Okay, because you are melting the ice, so you need to absorb energy in terms of heat, so it will be a plus sign. So this will be standard enthalpy of sublimation, where solid convert directly to vapor. Okay, example here, graphite convert to vapor. So the enthalpy, standard enthalpy value for this would be positive 716.68 kilojoule per mole. Next is bond dissociation enthalpy. Okay, again at standard. Okay, so dissociation of bond between A and B molecule. You get this symbol here. Okay, next is standard enthalpy of combustion. Okay, triangle shape with subscript C. Okay, enthalpy, standard enthalpy. Okay, so standard reaction enthalpy for the complete oxidation of an organic compound to carbon dioxide and H2O if the compound contain carbon, hydrogen and oxygen. Okay, and if you have additional, for example nitrogen, if N is present in the compound. For example, combustion of glucose here. Okay, so it will form carbon dioxide on and H2O. Okay, so the enthalpy of combustion for this compound will be negative 2808 kilojoule per mole. Next is standard reaction enthalpy. Okay, so you see this symbol here. So this is change in the enthalpy when reactant in their standard state change to product in their standard state. Okay, so if you have this reaction here, okay, we find the enthalpy. We use the enthalpy formation to find the enthalpy of reaction. Okay, find the enthalpy formation for individual product minus reactant. So we get enthalpy reaction change. So this is an exothermic process because negative. So next is ionization. So what is ionization? So it is a change on the atomic level where electron is removed. So we remove electron from a gas phase atom. Okay, that is for the first ionization. Okay, and then the second one will be the second ionization. For example here, this is a gas for X. So we remove the electron here. So we remove the electron, leaving the X become positive. Okay, and that would be the first ionization enthalpy. Okay, the subsequent removal. Okay, so we remove the following electron from the X ion here, X plus. So we get X2 plus plus A. Okay, remove electron. So that would be the second ionization enthalpy and so on. So enthalpy for removing an electron from a neutral atom, this one, okay, is always positive. So this process would be a endothermic process, okay, and it gets more positive when we remove the subsequent electron. Next is electron gain. Okay, so this will be another atomic level change. So in this case, electron is added to a gas phase atom. Okay, however, you cannot simply say that this will be the opposite of ionization, because why? Let us look here. Okay, so this is ionization process where we remove the electron. Okay, but if we reverse the ionization, we will get this. But then electron gain is this. Okay, you have the neutral atom. Okay, add electron, you get a negative ion. But the reverse of ionization just now, you didn't see any negative X here. Okay, although based on the definition it seems that way, but it's actually not. Okay, so enthalpy for adding electron to a neutral atom sometimes can be endothermic and sometimes can be exothermic. Okay, but ionization just now is always endothermic. Okay, so for electron gain, okay, e.g., the enthalpy change would be positive if the electron is added to a full shell or a sub shell. Okay, next is bond enthalpy. So this is another atomic and molecular level process. Okay, let's say you have gas phase reaction. Notice it's still in gas. So we have the X bond, okay, between A and X. Okay, so you get A and X. Okay, after dissociate the bond. Okay, the covalent bond. In this reaction, we name them bond enthalpy. Okay, so the enthalpy change for removing hydrogen from carbon, okay, varies from molecule to molecule. Okay, and even from H to H. Let's say if you separate H with C, you get a different value if you separate H with N, for example. Okay, so we get bond enthalpy value from table. Okay, and we can use that to estimate enthalpy change of a reaction. Okay, so this is the standard enthalpy formation. Okay, and normally this value are given to you in order for you to solve any question. Okay, so you see here, these are the substance and this is the enthalpy of formation. Even Gibbs free energy also given here, as well as entropy, and we will cover this in the following part of thermodynamics. Okay, so we can actually use the enthalpy of formation to calculate the enthalpy of a reaction. Okay, so let's say you start from reactant, Okay, start from the element to form the reactant. Okay, formation of the reactant from its element. Okay, let's say you are given this value and you are given this value. Okay, from here to here. So use this value here and you reverse the magnitude for this value here. Okay, example. Enthalpy from change for fusion of ethanol, okay, would be 4.60 kilojoule per mole, while the enthalpy change vaporization for ethanol is 43.5 kilojoule per mole. What would be the value of the condensation enthalpy change for ethanol, and also sublimation enthalpy change? How to solve this? Because you are given the vaporization, it's the opposite of condensation. So you just reverse the magnitude or the value. So if vaporization here is positive value, therefore condensation will be negative. How about sublimation? Sublimation from solid to gas. So therefore we use both fusion and also vaporization to calculate sublimation. So we can get 48.1 kilojoule per mole for enthalpy of sublimation change for ethanol. Next is using standard enthalpy formation to calculate the enthalpy change for reaction. Okay, given to you this reaction, okay, methane plus water vapor, you get carbon monoxide and hydrogen gas. So find the enthalpy change for this reaction here. So we use the enthalpy formation for individual compound as well as element here to find the reaction. Okay, so given to you individual, so you can calculate the change. Okay, product, sum of product minus sum of reactant. Next is using standard enthalpy formation to calculate enthalpy of combustion of propane gas to carbon dioxide and water vapor. So this would be the reaction. Okay. Okay, so using the enthalpy change for formation for individual compound as well as element, so we can calculate enthalpy change for reaction. Okay, this one you can look up in the standard table.